Welcome to Lecture 15B, entitled Triple Integrals and Cylindrical Examples, Cylindrical Coordinates, and again, we're going to work out a number of examples. This lecture basically makes use of material from section 16.5 of the text, and also some reference to material in section 3.2 of Reading Assignment 2, which is not necessary to look at, not mandatory. The objectives are understand worked out examples from the textbook, and again, the concepts and visualization skills are integration bounds for radius r, angle theta and z, visualization of bounding surface in cylindrical coordinates, and the differential volume in cylindrical coordinates. As usual, the second slide basically is just a summary of the slides to follow, so we'll just move on. All right, so here's our first problem. The problem statement is to evaluate the integral I is equal to integral 0 to 2 root 2, integral minus square root 8 minus x squared to square root of 8 minus x squared, and integral minus 1 to 2 of the function square root of 1 plus x squared plus y squared dz dy dx. So again, this is a setup in Cartesian coordinates, and so first step is to figure out what does this object look like. So if we look here, this dz refers to this integral, dy refers to this integral, and dx refers to this integral. All right, so dz basically is from z equals 2 to z equals minus 1, so that would be a plane at z equals 2 and a plane at z equals minus 1. So that's that upper surface and then the lower surface down here. The next is y equals square root of 8 minus x squared, on upper bound 8 square root of minus square root of 8 minus x squared. So this represents a semicircle of radius 2 root 2, and this represents a semicircle which is negative. That's the other side of the semicircle, again radius of 2 square root 2. And this would then have a z value which extends to infinity, so effectively it's a cylinder. So this is what you see as a portion of that cylinder which would extend to infinity. And finally, the last thing we would have is x from x equals 0 to x equals 2 root 2. That means y and z could be anything. So this would be a plane that's parallel to the yz plane at different values of x. And so this is what we basically see, the yz plane being the backside there. And so you're going from there to some point out here, which is at 2 root 2 along the x direction. Right, so if you then take those surfaces, put them together, then everything inside is the region of interest. And so this is the picture that we end up with in terms of the volume. It's half of a circle, but we're only basically looking at quadrants 1 and 4 as being part of this domain. Now, down here, you can sort of look at basically the region, either with respect to the xy plane or with respect to the r theta plane. And I've done two different approaches here. This one essentially shows in Cartesian coordinates, and this is an overlay, which is in Cartesian coordinates, but using polar coordinates to indicate what the radius looks like and what the angles look like. This is a clear r theta plane, which is always going to be basically involving straight line segments as shown here. So in this case, what you'll see is the lower bound on this region is y minus 8 minus x squared square root, and this being the upper region is y square root 8 minus x squared. The bounds on x would be x equals 0, which is this line that you see here, and the upper bound would be x equals 2 root 2, which is the line that you see here. So everything sandwiched between this contour, and this contour here is the region, which is this gray part that you see. You could also have drawn the same picture, but indicate what r is. Well, r basically goes from 0 to 2 root 2, and theta would sweep from minus pi over 2 to pi over 2, sweeping out this region. If you do it in the r theta plane, then r goes from 0 to 2 root 2, and theta goes from minus pi over 2, which would be down here, to pi over 2. So this would be sort of like a rectangular object. So different ways of visualizing it, but this is the object that we're interested in. All right, and so there, if you want to look at an interactive demonstration of the problem, you can look here. You'll find something that might be useful. All right, so we're going to now solve this problem in cylindrical coordinates. So first, let's make use of the coordinate transformation. Here it is, x equals r equals theta, y equals r sine theta, z equals z. And the integrand is just 1 plus x squared plus y squared. So to convert this into cylindrical coordinates, we make use of the transformations. We substitute those in here, and we end up with r squared cos squared plus r squared sine squared, which is nothing more than r squared. So this is now the function in terms of polar cylindrical coordinates. The bounds on z basically remain the same, so it's minus 1 is less than equal to z is less than equal to 2. And the region of integration in Cartesian coordinates was basically plus or minus 8 minus x squared, or you could effectively write this in the equation form as x squared plus y squared equals 8. And the limits on x were from 0 less than equal to x less than equal to 2 root 2. If we look at this in cylindrical coordinates, then this would have been r going from 0 to 2 root 2, as shown on the previous slide, and theta would range from minus pi over 2 to pi over 2. So we now have the bounds for the region, and we have basically the bounds for on z. So we can put them all together and basically write out the integral in cylindrical coordinates. So there are the bounds on z. There's the bounds on r, and there are the bounds on theta in that order. So dz, r, theta. So we just have to integrate this. We integrate first with respect to z, which means this just becomes z, so it's 2 minus 1. That gives you the value of 3. And then the remainder is just now to integrate with respect to r, holding theta constant, and then finally integrating with respect to theta, and you end up with an answer of 26 pi. All right, so let's look at a second problem. This is to find the mass of the cylinder d bounded by the paraboloid z equals 4 minus r squared, and the plane z equals 0, where the mass density of the solid in units of kilograms per cubic meter, given in cylindrical coordinates, is 5 minus z, which means we're dealing with an object which is heavy near the base and light near the vertex, that is near the top. So here you'll notice that the paraboloid has already been given in cylindrical coordinates, so we don't have to do anything specific with it. And the plane z equals 0, that's fine. That's also in cylindrical coordinates. And so we're going to basically now find the math, but we're going to do everything in cylindrical coordinates. Notice here in this diagram below, this is to show you, for instance, we're integrating first in z. So that would be basically looking at the height between the z equals 0 plane and the surface of the paraboloid. And the second diagram here is, having done that, integrating over the region. So that means we'd be integrating over r, and we'll be integrating over theta. So this is the first integration with respect to z. After having performed that, then we'd be integrating over the region. All right, here's an interactive demonstration of problem 2 if you'd like to look at it. And so now we can carry out the calculations. So the integrand was a given, so we don't have to do anything with it because it's already in cylindrical coordinates, 5 minus z. The bounds on z, the lower and upper surface, z equals 0, and z equals 4 minus r squared. This is the z equals 0 plane, and this was the paraboloid. So that's the second one. The bounds in r, what are they? We equate the upper and lower surface, that's basically this, and solve for r. So 4 minus r squared equals 0. So solution for the upper limit on r is r equals 2, right, which is obtained from this solution. R equals minus 2 has no meaning because r has to be greater than 0, and the lower limit of r will be 0. So now we basically have everything we need. We also have the fact that we're going once around the circle, so that means theta goes from 0 to 2 pi. So here is the region of integration, and for the value of z, here's the upper bound on z and the lower bound on z, and here's the function already in cylindrical coordinates. So we can put everything together. Here's 5 minus z, dz, upper bound on z, lower bound on z, upper bound on r, lower bound on r, upper bound on theta, lower bound on theta. Integrate first with respect to z, holding r and theta fixed, and then we integrate with respect to r, holding theta fixed, and finally, working through this 3 different integrations, we end up with an answer of 88 pi over 3. All right, third problem. Let's find the volume of the solid between the cone z equals square root of x squared plus y squared and the inverted paraboloid z equals 12 minus x squared minus y squared. Now in this example, we've basically given the information in Cartesian coordinates, so we're going to have to transform these equations into cylindrical coordinates. That'll be part of the problem. So let's look at the picture. Here's a picture involving just a description in Cartesian coordinates. So the cone would be just z equals the square root of x squared plus y squared, which you see here. And the paraboloid would be this 12 minus x squared minus y, what you see here. So you integrate with respect to z first, which means you're going between the lower surface and the upper surface. All right, and then finally over the region, and the region would just be basically the projection of this contour, which is the intersection between the cone and the paraboloid, projected onto the xy plane. And in this case, r would be basically, the radius of this circle, and theta would basically extend from 0 to 2 pi. So that's more or less basically how the problem would be set up. And so what we can do now, after you want to take a look at this URL, if you want interactive version, we can then basically solve the problem. Okay, so the integrand, fxyz equals 1, it has no units. So we set it to 1 since we're interested in the volume of the object. We'd just be integrating dv, which gives you the volume. So as before, the cylindrical coordinate transformation has this form. Bounds on z basically we have already established. In Cartesian coordinates, the lower bound was square root of x squared plus y squared, which was the cone. The upper was 12 minus x squared minus y squared, which was paraboloid. And if we convert these now into cylindrical coordinate system using these transformations, the first one becomes z equals r, and the second one becomes z equals 12 minus r squared. So these are the upper and lower surface in cylindrical coordinates. The region r on the xy plane is determined by the intersection contour, which is obtained by equating the upper and lower bounding surface. That means equating this with this. Turns out the only solution that's valid is r equals 3. Therefore, the region r is from 0 to 3. It's with respect to r, and you do a full circle, so theta is from 0 to 2 pi. Note, the solution for r was obtained by solving the quadratic equation r squared plus r minus 12 equals 0. All you have to do is basically, when you equate these two together, you'll end up with r equals 12 minus r squared. Put everything on one side, and you'll end up with this quadratic equation. You'll end up with two solutions, r equals 3, r equals minus 4. Of course, this makes no sense since r has to be greater than or equal to 0. Therefore, the only possible solution is r equals 3. So that's the justification for this statement here. All right, so now we can put them all together and come up with the integration bounds in cylindrical coordinates. R goes from 0 to 3, theta goes from 0 to 2 pi. Lower bound on z is r, upper bound on z is 12 minus r squared. So these now can be plugged into the integration bounds on the integral. And here you see it. So we're integrating with respect to z first, so that would be this inner integral, upper surface, lower surface. Then we integrate with respect to r. Upper is 3, lower is 0. Again, in this case, remember these are all surfaces. So if r is equal to 3, right, that means basically that theta can take on any value from 0 to 2 pi, and z can go from positive infinity to minus infinity. So effectively, it's a cylinder of radius 3, and this would be a cylinder of radius 0. And finally, the last one was the angle from 0 to 2 pi, in which case r can be anything, from 0 onwards, and z can be any number up to positive or negative infinity. So that would be another surface. So this would be essentially a half plane that basically just rotates around to make a full surface. Right, so then we basically make the substitution. We've made the substitutions. So now we integrate dz r dr d theta. And so the first one will be just this minus this after integration. Then you integrate with respect to r holding theta fixed. And finally you integrate with respect to theta. And you end up with an answer of 99 pi divided by 2. All right, so fourth example. This is a little bit more unusual in terms of how the problem is set up. So we basically want to use cylindrical coordinates to calculate the volume of the region E. E in this case is set up in terms of inequalities. And this is how it's defined. In this particular integration that you'll have to perform, you'll need to make use of this integral. This type of information will typically be given to you, so you're not expected to memorize any of these things. This object, if you were to graph it out, would look like this, and you can click on this URL if you want to visualize it. Anyway, so it's something of interest, maybe of interest to you. All right, so the next thing is to solve the problem, that is example problem 4 solution. And this problem is to be done in solved in cylindrical coordinates, so we'll use the cylindrical coordinate transformation, which is x equals r cos theta, y equals r sine theta, and z equals z. The domain, E in this case, is based on the first 3 inequalities, and those 3 inequalities define the 6 boundaries. So again, I've stated them here, and so these are the inequalities we have to work from to come up with the 6 boundaries on the triple integral. So we have the boundaries on z to establish, boundaries on r to establish, and the boundaries on theta to establish. We start with the simplest being the fact that we're already given bounds on z, so explicitly, and so we might as well just write that out right away. So bounds on z would be an upper bound of 2, and then a lower bound of 2, and an upper bound of 5. For the boundaries on r, we convert the equation xyz less than or equal to 1 into cylindrical coordinates by substituting x equals r cos theta and y equals r sine theta. After some simplification and making use of the trigonometric identity that sine 2 theta is equivalent to 2 sine theta cos theta, we obtain this inequality, which is 1/2 r squared sine 2 theta z is less than or equal to 1. And we know that r is always greater than or equal to 0. Therefore, the bounds on r, the lower bound would be r is 0, and the upper bound can be obtained by basically just dividing through in this expression such that you have only r on one side and then taking the square root. 1 over sine 2 theta is equivalent to cosecant 2 theta. The 2 comes on top and z goes down below. So these are the bounds now on r, but in terms of theta. You need to come back to confirm that the argument of the square root is greater than or equal to 0. And so we will have to first figure out what the ranges on theta are to see whether or not this square root is greater than 0. We know z is greater than 0, so it's just a matter of establishing that the numerator is greater than 0. So the last thing is the boundaries on theta. And so we take the third equation, which is y less than or equal to root 3x less than or equal to 3y, and convert it into cylindrical coordinates. So again, you substitute for x, which is r cos theta, and for y, which is r sine theta, and you end up with the expression that's shown here. The next thing is to divide all sides through by root 3 r cos theta, and we obtain 1 over root 3 tan theta less than or equal to 1 is less than or equal to root 3 tan theta. But this inequality can be rewritten as tan theta is less than or equal to root 3, and 1 over root 3 is less than or equal to tan theta. So that's another way, basically, if you want to put it in terms of theta, take the inverse. You end up with theta is less than or equal to pi over 3, and pi over 6 is less than or equal to theta. You can take these two and write them in more compact form and say that pi over 6 is less than or equal to theta, which is less than or equal to pi over 3. Well, now that we know the range of theta, we can determine what the range of cosec 2 theta is. And for this range, it turns out that the cosec 2 theta is a positive value, and as a result, the square root here is also positive. So now we have the bounds. The bounds on z are 2 and 5. The bounds on r are 0 and the square root of this argument. And the bounds of theta are pi over 6 and pi over 3. So this is now just a matter of substitutions. So there's the bounds on r, then the bounds on z, and the bounds of theta. Remember, we have to make sure that when we do r, this has to be a function of theta and z. The next one basically cannot have r in it anymore. And now r is being taken out. So this could only be a function of theta. Okay, in this case, they're constant values, which is fine. The rest just becomes integration. So you basically would first do the r dr d theta. This will be r squared divided by 2. Right, and so that means you take this, square it. The 2 will cancel because you're going to get a half factor in the 2 here, and you're left with cosec 2 theta over z. And then basically integrate with respect to z, holding theta constant, and then finally at the end, basically integrating with respect to theta. So here, of course, we've made use of the integral that was provided to us a few slides back. Okay, so as I said, the order of integrations follows from the functional relations of the boundaries. Now I just want to make one last comment here. The main purpose when you have these complex integrals, triple integrals, is to get you to understand how to set up the boundaries. In many cases, we're not going to ask you to solve the integrals because they can be quite unwieldy and they can take up too much time, and in effect it's really not serving any real purpose if one had the time when one could do it. The main thing here is to understand what the region looks like, how to set up the bounds, understand what the Jacobian is. I think that if you can do that, I think you've more or less mastered the material. Okay, so that basically concludes lecture 15B. Thank you for listening.